Stewart, and I work at Exida, and I'm going to be giving you a presentation on mechanical failure rates, static versus dynamic operation. We're going to go ahead and get started now. Okay, so first of all, audio is provided from the internet, so hopefully you all can hear me. There's a question and answer tab at the side of the screen, so if you have any questions, pull out the side screen and type them in the box. I'm not the best at checking them throughout the presentation, but I'll definitely take time afterwards to answer any question, and if I remember throughout the presentation, I'll look over, but sometimes I get going and forget to look over, so please bear with me with that. And also, there will be a recording of this session available on our YouTube channel and on our website, and a copy of the slides will be emailed out to you the end of this week. So just so you know, you'll have a copy of the slides, and you can watch the recording anytime you need to. So once again, my name is Loren, and I will be talking about the mechanical component failure rates, static versus dynamic operation. A little bit about myself. I'm a CFSP. I graduated from Virginia Tech with a BSME, and I started my career doing custom design and manufacturing, and I continued on to Exida, where I now work with the mechanical customers. I do FMEDAs and audits and safety cases, along with continually researching and publish reports on Stiction, along with our 2H initiative. A little bit about who Exida is. We were founded in 1999, and we have offices all around the world. So wherever you are or wherever your customers are, we have an Exida office close by to you. And as you can see, we added a new one. Exida Japan is now an office, and we're very proud to expand to Japan. A little more about Exida. We have 4 major industry focuses. We have the OEM side, the system designer side, the end user, and the engineering contractor. As you can see, we have different tools and different teachings and different supports in every industry focus that there has to do with functional safety. And not only do we have the 4 main focuses, we also have main products and service categories. As you can see, we do consulting in IEC 61511, 62061, and ISO 26262. We also consult in alarm management control systems, security, and ISA S99. Along with consulting, we have product certification, and that is to IEC 61508 in functional safety, and we also do product certification with cybersecurity and network robustness. Along with consulting and product certification, we have training. You can come to us, we can come to you, however you would like to be trained, we can train you. We have many different courses that we have available, and however you want to be trained, we will make that happen and make it work. We also have engineering tools and reference materials. We have Excellentia product, our SIL alarm, and our LOPA and SIL verification tools. We have our safety case and FMEDA tools, as well as our databases, our textbooks, and tutorials. Along with all of that, we also have our professional certification program. We have our CFSE and CFSP program, which stands for Certified Functional Safety Expert and Professional. And this is a little bit more about our products. We have our FACS, which is Process Hazards Analysis, hazard and operability studies. We have our Excellencia program, which is SIL verification, selection, SRS, and proof test generator. We have our SERH viewer, which is our safety equipment reliability database. Our SIL alarm product, which is alarm rationalization and master alarm database, and SILStat, which is a newer product, which is a collection and analysis of operation and maintenance safety data. So along with all of our products, we have our reference materials, and we're really proud to announce that we have authored most industry references for automation, safety, and reliability, along with we have our industry data handbook on equipment and failure data, and we've authored the most comprehensive book on functional safety in the market. But now let's get down to what you came for, which is the webinar on mechanical component failure rates, static versus dynamic operation. So our first key point we're going to make today is the failure rates of certain mechanical components used in solenoid valves, actuators, and valves may vary substantially depending on the operation. So for example, seals such as O-rings have fundamentally different failure modes when used in applications with frequent movement, such as a dynamic operation, versus applications with infrequent movement, which would be static. We're also going to talk about how exida has accumulated over 100 billion operating hours of field failure data, primarily from the process industries, which was used in recent mechanical failure research. This webinar will explain some results from this research that exida conducted, where the failure rates and the failure modes of several mechanical components were established. So to understand this, we're going to first look what it means for static and what it means for dynamic applications. So a static application is defined as stationary or fixed. So it would be a low demand mode of operation, such as being in a safety system or something that only moves once or a few times per year. Dynamic applications are defined as energetic or capable of action or change or forceful. What this means for functional safety and for valves and actuators is would be a high or a continuous mode of operation. So we're going to also look at mechanical failure data sources and how you get mechanical failure rates and where all of these come from. So there are four major categories of how to receive failure rates, failure data. The first one we're going to look at is an FMEDA. And as you can see, there's positives and negatives for all of the different ways to collect data. But the FMEDA, the positives is it can provide detailed and complete information. It's a predictive application and does not require a multi-year lag time to gather statistics. But the minus of it, it depends on the component failure mode and failure rate data. So the old saying goes, garbage in, garbage out. If you're using failure modes that are not competent or do not have enough information in it, or the failure rate data is bogus, it's what you use is what you're going to get. The next way of collecting mechanical failure data is end-user field failure studies. The major plus of this is it's real data. That's awesome. But the variations of the amount of data collected is huge. There's different definitions of failure if you go from company to company. Some might consider something a failure where other companies won't. And another minus is it's categorized, and merging technologies make it not consistent. The next failure data source is manufacturer field return data studies. Once again, huge positive is it's real data. The minus is its calculation methods vary widely. Once again, company to company, you're going to get huge variations. Also, you cannot know what percentage of actual failures are returned. If it is a low dollar item, you might not get a return. It might just be something, it would be easier for the company to throw away and order a new one rather to let you know that a product is being returned. And once again, each company has a different definition of a failure. Some might be more specific. Some might just say everything's a failure, and some might say, oh, we don't want our failure to look bad, like we get a lot in, so even though these are failures, we're not going to count them. And finally, for mechanical failure rate data source, you have cycle test data. And this is based on cycle testing for mechanical or electromechanical products. And the big thing we're going to look at is it assumes the application has a constant or dynamic operation. So for high demand or constant demand applications, that's great. The first one on the list is a FMEDA, so we're going to go ahead and look more detail in what a FMEDA is. FMEDA stands for Failure Mode Effects and Diagnostic Analysis. So what it is you gather enough failure statistics at the product level, and gathering all of that has not happened. You have failure causes, failure modes, etc. are all mixed together in failure reports. So therefore, a break problem, you want to break the problem into smaller pieces is what the FMEDA does. And it is perform a detailed study of each component and how the component failure rates will affect the instrument. So from the bill of material, we look at each nut, each bolt, each seal, and figure out all of the ways that can break. And using our component database, the failure rates and the failure modes for the product, that can be determined far more accurately than only with the manufacturer's field failure data, because you don't know what all is returned, you don't know what all you are getting in. So you take each component of the bill of material, you have a failure rate number from that, and you add all of the components up, looking at each failure mode distribution and each way it can break and all of the failure modes, and that's what you get when you make a complete FMEDA. And you also look at the diagnostics, whether it has, if you're going to perform a partial valve stroke test, a full stroke test, it depends on the diagnostics, and that is taken into consideration in the FMEDA as well. So with all of that information, you are able to then come out with the full product failure rate, which is the lambda, the product failure modes, and the full product diagnostic coverage. And with FMEDA, they're also validated results. So you take all of the information from the FMEDA, which is now on the right-hand side, and you compare that to field return studies that are done, which are on the bottom. So you always want to have your FMEDA slightly more conservative than your proven in use study or the field return study. You don't want to underestimate the product failure rates and the diagnostic coverage. So it's a good thing when you are not getting as many returns or your system is better than the general or the assumed. So every FMEDA that we do, we check it against the field return studies performed for every existing product. And so we make sure that the FMEDA is a validated result and that the FMEDA is in line with what you are seeing. So once again, this is the same slide. We just learned what a FMEDA was. And we talked about field failure studies and checking that against the FMEDA. Next, we would talk about manufacturer field return data studies, which I think is pretty self-explanatory. It's, once again, real data, but it depends from company to company how they're getting their information in and what they are deciding what a failure is and the percentage that are actually coming back to you. So now we're going to take a look at cycle test data and cycle test scaling. So cycle testing is used to estimate high failure rates in dynamic or a high demand or continuous demand application, which if you're in a manufacturing plant and that's what your valve is going to move constantly or multiple times per day, this is a great estimate to use. But you have to assume but cycle testing assumes that premature wear out is the dominant factor in failure mechanisms and that no other failure mechanisms are significant. And we're going to take a look at what other failure mechanisms that might be significant besides premature wear out. So this is one example of a certificate that we've come across recently. And as you can see, when you receive a FMEDA and your failure rates, you're mostly going to be concerned about your dangerous failure rate. So this highlights a dangerous failure rate, and this is showing as 8.54 fits for an entire valve actuator assembly. And to kind of put that in perspective, that's saying that you're going to have, for an entire valve and actuator, you're going to have the same dangerous failure as 1 volt or 1 resistor. One O-ring is much higher than 8.54. So when you're looking at dangerous failure rates, please make sure that do a sanity check before just using numbers in your calculation. One of the theories behind such a low number is that possibly cycle testing was used. And as you can see, this failure rate is over 40 times lower than what, if you go ahead and do a FMEDA, that the failure rate would come out to. So one of the theories behind this is actual cycle testing, which is fine for a high demand or a continuous demand application, but not for a safety system or something in a low demand application. So when you receive a certificate or you look at the failure rates of a dangerous, when you look at the dangerous failure rate of a valve, an actuator, anything, make sure you do a sanity check and say, does this make sense? With my knowledge, with what I've seen in the field, can this be possible? So to once again go back to all of the ways of receiving mechanical failure rate data, we're going to look at the comparison of a solenoid valve. So the first source we're going to look at is one of the exida FMEDAs, which is a solenoid valve. And we found the dangerous failure rate per hour, which E times 10 to the negative 9 is in fits. So this is 159 fits. The second example is a spool valve, solenoid valve, which is coming out to 566 fits, or 5.66 times 10 to the negative 7. If we look at, this is actual field data in a chemical plant, this plant study had a solenoid valve, and they were coming out to 3.15 or 51 times 10 to the negative 7. Another company is the FMEDA published data, and it is looking at a solenoid valve as 9.00 e to the negative 7. And that is the highest number, but it's because they don't necessarily break apart their products in a clean condition or a severe condition. They don't break it apart into further looking. So that is a very conservative number, but hey, being conservative is a good thing. Next, we're going to look at a cycle test result for a solenoid valve, and it is only 8.59 fits, so 8.59 times 10 to the negative 9. That's an extremely low number. Like I said, that's the same, about the same value. Our studies have concluded that one single bolt or one single screw would come out to. A second cycle test result came in for a solenoid valve at 0.45 fits, which is, that's not even one washer. It's the lowest number on our comparison study. And then we also have a manufacturer or warranty data coming out to 17 fits, or 1.7 times 10 to the negative 8. And once again, sometimes with manufacturer warranty data, you don't know what all is returned. You don't necessarily have all of the information. So we can see that that's a little lower than FMEDA's or the actual field data. But once again, it's good that the FMEDA's or the other actual data is a little conservative. So comparing the failure rate data from the process industry calibrated FMEDA results and the field failure data results from the process industry to cycle test results. So this is, like I said, comparing everything together in one chart to make sure, to make you aware and to make sure that when you're comparing the different mechanical failure rate sources, you know about what to expect and you're educated on the process. So we're going to talk about low demand application hazards. And while cycle testing is great, it's for high demand or continuous demand applications, using it for a low demand mode is dangerous. Low demand applications generate failures that high demand applications do not see and do not develop. While in an inactive state for long periods of time, such as a safety system would be, issues such as stiction can transpire. And this is one of the topics that I've done a lot of research on. So what is stiction? Stiction is a combination of static plus friction. It is the resistance to start of motion, usually measured in the difference between an external force being applied in order to overcome the static friction and the force to maintain the movement between the two contacting or working surfaces. This can result from corrosion, cold welding, a breakdown of lubrications, a buildup of deposits, chemical reactions, a breakdown of sealing components. There's many reasons why stiction happens, but it's something that is happening, and that's what you need to be aware of. I've actually gotten the question, well, no offense, but who really cares about stiction? Well, we do. Exida has studied stiction to determine the maximum amount of time period before stiction impacts the failure rates. And this is the maximum time period for scaling cycle testing results. So the real impact of stiction is that time period. And we've discovered that stiction becomes significant after 1 week Therefore, you should never scale cycle test results beyond 200 hours. So after 200 hours, the stiction or the static plus the friction time period, it starts building up, and that's when it becomes significant to failure rates. We've also discovered that improvements in safety and reliability can be obtained with stroke testing. So this is a picture of just a pretty generic solenoid valve. As you can see, the dark portions in here are O-rings and places that, as you can see, there's a lot of O-rings in a basic solenoid valve. So all of those places that an O-ring has, or any mechanical components that are touching and have a long time period without movement, stiction can start. So we're going to look at the evidence of stiction and who says there's really this stiction. So first we're going to start with expert knowledge. So if you go around to any plant or any manufacturing place, you can talk to technicians, you can talk to engineers, you can talk to those experts that routinely work on valves and say, do you notice anything, what's going on? And they usually say, well, it's about a week or 2 weeks or something like that. After that, if you want this valve to move, you gotta bang it with the hammer, or you have to jump start it somehow. And then it works fine after that. So you're just gonna have to come with a sledgehammer, hit it a couple times, and you're good to go. Next, we're going to also look at O-ring manufacturers' guidelines. And if you look through the big, thick user manual that they give out, they say if it's stationary between 1 week and 1 month, delays between cycles happen. So the stiction happens, and delays between cycles plateau at approximately 300 hours, which that's about what we saw also. So who else has looked at stiction? There's been many experimental studies. Studies have concluded that on lubrication thickness in magnetic thin filmed discs, as equilibrium rest time increases, so as you're not moving, stiction increases, and it starts to plateau at about 275 hours, depending on the lubrication type and thickness. So 275, 300 hours, about a week. This is all kind of lining up. But if you want another example, look at ISO 13849, and it says that a valve must be operated at least once per week or once per shift to ensure the intended function. So all of these different experts and manufacturers all agree within about the same period of time. So now we know that stiction exists and a lot of people believe it. What's the impact? So the impact is failure results when forces are insufficient to move mechanical parts as designed. So you have a valve that could be stuck open. There could be environmental variables impacting the rate of friction buildup. Therefore, stiction is treated as stochastic, I can't say that word, I'm sorry, variable for failure rate analysis. And once the stiction is broken via a movement of friction, the friction or stiction starts building over. So if you have a valve and you do stroke it, you take the stiction back to a zero position and it starts again. So if you want to break this stiction or this friction barrier, if you just move it, it's going to undo the impact of stiction and you're going to start over. So what does this mean for failure rates? So we're going to look at the impact of dynamic versus static failure rates.
So these values of an FMEDA failure rates from a solenoid valve. So this is, of course, we can't say who this is, but it's manufacturer X, model Y. So we're looking at a specific manufacturer and a specific model of a solenoid valve. So our parameters are, you have a lambda D, which is the dangerous failure rate of stiction. You have a lambda D non-stiction detectable and a lambda D non-stiction undetectable. So just the lambda D stiction, which is all of the dangerous failures that can be contributed to stiction, is broken down into detectable and non-detectable. And as you can see, a lot and most of the dangerous lambdas or failure rates are stiction. So you have the lambda D stiction and the lambda D non-stiction. You have detectable and undetectable. So if you go ahead and break this stiction variable, most of your failure rates, 103/5, can then be contributed down to 0. So if you do something like a partial valve stroke test or full stroke and break the stiction bound, you can then take the dangerous failure rates of stiction and take that down to 0. So this is drastically improving your overall dangerous failure rate. So once again, this is a look at static versus dynamic operation. You have your static operation, which is the dangerous failure rates, which is lambda, the dangerous failure rate of stiction, the dangerous failure rate of non-stiction, broken up into detectable and undetectable. So you have the 103/5 from stiction, which we just saw, the 84 from non-stiction detectable, and the 1.9 to non-stiction undetectable. So this solenoid, the dangerous failures, would be 189/5. So if you have a frequent dynamic motion, you would only have the non-stiction detectable failure rates and the non-stiction undetectable dangerous failure rates. So your total dangerous failure for a dynamic operation would only be 62/5. So as you can see, it's less than half. So to wrap everything up, we're going to look at the recommended best practices. So because of stiction and other mechanical phenomena that happen, you can't use cycle testing for a low demand application unless you move it often as a high demand or continuous demand applications, or if you want to stroke test it at least every 200 hours, if not more. So in low demand applications where the mechanical device does not move at least every 200 hours, use FMEDA failure date or expert analysis plant failure data to come up with your dangerous failure rate so that you are not using dangerously low failure rates and you are not assuming that you're safe when an accident could actually occur. So right now I'm going to go back and look at the questions. Pull this open. Are there any questions at this point? Let me see here. Okay, I'm back. Sorry about that. Are there any questions at this point? Let me see here. I see that there is a question and it can't come out. Hold on. There we go. Let me expand this.
I'm sorry, I'm having a little technical difficulties. Okay, I think I have it now. Okay, the first question that I'm receiving is, are your recommendations included in safety standards? And I'm assuming that the recommendations that you're speaking of is the moving every 200 or so hours, and there are not included in the safety standards, although as you can see there are many studies and what's the word I'm looking for? There are many tests and studies done to agree with this, although they are not included in the safety standards. The next one is, my question relates to the driving product failure rates using FMEDA and exida component database. You stated that the failure rates of the solenoid valve using an exida FMEDA was 159 fits. And just so you know, that was one example of one solenoid that we did. My question is, how many components did you consider in this FMEDA for this building, i.e. the retaining clip, the solenoid coil, the core tube, the plug nut, and so forth? Let me start with that part of the question. We look at the entire bill of material, so every single thing for that one solenoid we looked at. And that, I know that example was a very simplistic solenoid. It did not have a lot of parts, so that is one of the reasons that was a lower. As you could see further on, we had another example of a solenoid valve which had a spool in it, and that solenoid was higher. So it depends on what is in the bill of material that we look at, but we take into consideration every single part in it. And some of the parts we may decide have no effect on safety, such as a handle for like, say you have a valve and you have a handle for a mechanically shut it, but it doesn't, for our safety function that we're looking at with an actuator, it would not use that, so we decided that that handle has no effect on safety. So we do look at every single component, although we might decide that in the safety function that we are using it as, it might not be considered it might not have an effect on safety because how we are using it. Okay, then the question continues on. How well matched these components with the exida component database? So has the database different failure rates for different plug nut models? So the failure rates in the exida component database, we have a book and it breaks it down for each component. We also have a component database on Excellentia, which is the entire valve or the entire solenoid, the entire actuator. So we use the exida component database to build the FMEDAs up. So we actually use the numbers for each component in the bill of material. And then the next part of the question, how does the exida database cater for different services, clean versus plugging? The exida, the component database we use actually has different services. So you have a clean service or a severe service environment, and we usually, unless it's stated that you're selling your valve only for clean conditions, we give out clean and severe services. Also, we have different environments. We look at if this would be an offshore application. We look at if this is going to be an application indoors, which has a pretty clean environment. We look at if this application is going to be deep sea or have a lot of corrosion capabilities. So we look at all of the services, and we cater each FMEDA to the way each product is going to be used. The next question is, how do we know if cycle test results have been presented to us as end users? My suggestion would look at the dangerous failure rates, look at the numbers. And as an end user, you're going to be, you have to use a little common sense. You're, I'm sure, a smart guy. Look at the dangerous, especially the dangerous failure rates. That's what you're going to be most concerned about if your application is going to be in a safety system. You want to make sure that if it fails, you don't want it to fail safe, but you really don't want it to fail dangerously. So look at the dangerous failure rate numbers and decide, does this make sense? Presented with the dangerous failure rate number, you'll also have a mean time to fail dangerously. And does it make sense that a valve that you're going to buy says it's only going to fail once in 100 million years? That doesn't make sense to me. How could it, so it is guaranteed never, ever, ever to fail, nothing's going to happen? So take a look at the failure rates, take a look at the mean time to fail dangerous, and see if this makes sense to you. Just use your common sense and then ask more questions. It might not be always a cycle test that you have to be concerned about, but what you have to be concerned about is using overly optimistic data. I always joke that if, as engineers, you have to be concerned about ethics. If you are given a number that is wildly unrealistic and you use that, what are the ramifications of that? This valve could be called into practice and it needs to close off the process, and if that doesn't close off, what happens if there's an explosion? What if someone's close to that explosion? If you use unrealistic data, the ramifications of an engineer using unrealistic data are huge. There could be loss of life. If I always tease that if somebody such as in a marketing department uses unrealistic data in a brochure, you could be like, oh, our valve is the best, it's never going to fail. And you could have a tarnished reputation, or, you know, people not believing that or rolling their eyes. But if you're going to be in an engineering position and use unrealistic data, the difference could be a loss of life. So when you are given your numbers, do a sanity check. Just don't blindly use numbers. And if they don't make sense, ask questions. If you want to, take my email address down. If you have questions, email me. If it's something that is unrealistic, raise the red flag, because like I said, the ramifications could be huge. And you don't want that resting on you. The next question is, how would the recommendation for routine testing be portrayed in a safety manual, noting for low demand use? So if you're manufacturing a valve, say, when we go ahead and look at a safety manual, we always make sure that the safety manual says for low demand use. And as a manufacturer, you want to make sure your customers know that it is for a low demand use, and these failure numbers are for low demand use. If it is a valve that is still rated that could be in high demand use, you could give them a high or continuous demand use numbers. But in safety manuals, we like to see a section for proof testing. how often you recommend proof testing because of a low demand or safety demand application mode. So I would always note it in the safety manual. Of course, it's up to the end user to follow your instructions or not, but you as a manufacturer always have the, you always can recommend, these are the steps for proof testing. This is how often we recommend you proof test. It's a low demand mode, but this is why we recommend. So I would definitely portray it in the safety manual, and just through proof test coverage numbers, and say if you recommend a full valve stroke, a partial valve stroke, and how to do this testing. The next question is, from the bathtub curve model, we expect that a cycle test failure rate to be higher, not lower than a continuous failure rate. Why is cycle test result only compared to that for a washer, for example? So, where did the question go? Hold on. From the bathtub curve model, yes, we expect cycle tests to be higher, not lower than a continuous failure rate. Continuous and high demand are fine for cycle testing. What we were comparing it to was the low demand failure rate of, for example, the washer. So if it is high or continuous demand, that is fine. The cycle test results that we have to be aware of come from when it's in a low demand application. And the final question we have, can you send me a copy of the slides? Yes, everybody is going to receive a copy of the slides in a follow-up email later this week. I hope everybody enjoyed the webinar, and if you have any questions later, let me know. Thank you, and enjoy the rest of your day or night, depending where you are.